Before we look at Green's theorem, I want us to look at some notations that will help us in studying the theorem. So, for instance, if we have r of t as x of t, y of t, z of t, where t is between a and b, assuming this is the parametric equation of a curve in R3, for instance, the notation for r prime of t, or r prime of t, will just be to take the derivative of each of the components of r of t. All right, and in that case, so this is one notation. Another notation, I mean, this is not a notation, it's obvious. So another notation is this: the r is the same thing as dx, dy, dz. Okay. But what is dx, dy, dz? Dx can be written in terms of x prime of t as x prime dt, x prime of t dt. Dy is y prime of t dt, and dz is z prime of t dt. All right. Okay, so these are the notations. This is the main notation I want to actually introduce to you. So whenever I say the r, I mean the x, dy, dz is the same thing as x prime of t dt, or y prime of t dt, z prime of t dt. So for instance, if for instance we have f of x, y is a vector field which has the component f and g, both of which are functions of x and y, then the line integral of f along a curve C may be written as line integral C f dot t ds. We know this, we've used this notation, or f dot dr. We've used this notation before. Or now that we have another notation, we have the dr notation, right? And we know f is f and g, right? F is the first component and g is the second component. If we do that, if we dot f dot dr, then we get f dot the first component of dr, which is just dx, so f times dx, sorry, plus g times dy. Okay. So I just want us to know that there are now three notations for line integral, and they are all valid depending on the scenario or what you have in the problem. Oh, no. No. What am I doing? What is I doing? All right. Okay. So now we're ready for Green's theorem, Green's theorem, if we let C be a simple closed smooth curve, and the smooth curve is oriented clockwise, and let's assume that C encloses a connected and simply connected region. R. Okay, so what would be this scenario? So we have C, something like this, oriented in a counterclockwise direction, and then we have R, simply connected, a connected region. All right. Then, if we also assume that F is a vector field with components little f and little g, where f and g are continuous functions that have continuous partial derivative. Let's say they have continuous partial derivatives. In R. Then we have the Green's theorem. Okay? Green's theorem states that the integral, line integral along C, and it's a closed region, so we can put this notation here. Line integral is, which is f dot c ds, which we can also write as that f dot dr, right? Which we can also write now as f dx plus g dy. This is equal to the double integral over R dg dx minus df dy dA. Okay. All right. So this is Green's theorem. The big part of Green's theorem, the main part that everybody remembers, that you should remember, is just this part. This is your Green's theorem here. Green's theorem basically is a way of expressing line integral in terms of double integral. That's what Green's theorem does. Examples. Before I go into the examples, I just want to mention that the proof for the Green's theorem is very beautiful. I choose not to do it here because I wouldn't have time for it on the video. I like short videos, even though I haven't been very successful in making my videos shorter. But I would encourage you to look at it. It's everywhere. So we have f of xy as negative yx. It's a vector field. We would like to evaluate the line integral f dr, where C consists of the line segments 0, 1 to 0, 0, and then 0, 0 to 1, 0, and the parabola y equals 1 minus x squared from 1, 0 to 0, 0 or 0, 1. Okay, so let's look at what we're dealing with. We have the region this is our x-axis, y-axis, and this is our x-axis. Okay, we have the region, the line segment from 0, 1 to 0, 0. So this is 0, 1 here, and then we're going to 0, 0. Then from 0, 0 to 1, 0, and then from 1, 0 to 0, 1 again. Okay, so we have the line segment here, call this C1, then another line segment, let's give them different colors, another line segment here, call it C2, and then the parabola, like that, call this C3, okay? So we can now start by parameterizing these curves. And I'm going to give you the parametric equation of the curves. I'm sure by now you are able to get them yourselves. So C1, let me do everything in bright blue. C1 is let's call it R1, and it goes from 0, 1 to t times 0, negative 1. So the direction vector is 0, negative 1. So this is just 0, 1 minus t, okay? And since it's a line segment, we use the equation of a line segment. C2 is R2, and it's 0, 0 plus t times 1, 0, and it is t, 0. And then we have C3, which is R3. We call it R3. It's 1 minus t, then 1 minus t squared. Okay, I'm going to explain. So let me finish, then I'll explain. This is 1 minus t, 2t minus t squared. Okay, why? Because I want my parameterization for all of them to be from t between 0 and 1. The first curve is easy to do. The second one, it's easy. The third one, you have the parabola y equals 1 minus x squared. What I did is I chose a parameterization that I'm comfortable with, that I know about. I chose the parameterization x equals 1 minus t and y equals 1 minus t minus 1 squared, since x is 1 minus t. Why did I choose this? Because I'm going from where x is equal to 1 to where x is equal to 0. So I chose 1 minus t because when x is equal to 0, when t is equal to 0, I want t equals 0 to be here, and x and t equals 1 to be there. So when t is equal to 0, x is equal to 1. When t is equal to 1, x is equal to 0. So I hope it makes sense why I chose this parameterization right here. Okay, that's the only reason why. Let me write this in pink to make everybody know that I'm just talking about the pink curve. Okay, and I could also do this in pink. Why not? All right, so that makes sense now. I'm gonna take it all the way here. Put it there. Okay, so we have our parameterization, and we know that we're doing our integration of the vector field along C, and C is a combination of C1, C2, and C3. Okay. Now, I am not, never mind. Okay. I'm not using, well, let me say that. I'm not using the Green's theorem yet. I'm just doing what we already know. Forget Green's theorem for a minute, okay? So let's just do this integral without Green's theorem. We're going to come back and try to do it with Green's theorem. So this is 0 to 1, f dr. Remember how you compute f dr? This is just f of rt times or dot r prime of t, okay? So that's what I'm going to do in each of these. So if I do that, I get t minus 1, 0 here, dot 0, negative 1. I want you to check it, dt, plus 0 to 1, 0t dot 1, 0, dt, and then plus integral 0 to 1 t squared minus 2t 1 minus t dot negative 1 2 minus 2t. All right. Okay, so make sure you check all this and let me know if there was any mistake. So this integral, the first integral is 0 dt. Yay! 0 is a nice thing. 0 is very merciful. All right, 0 to 1. This is t squared minus 2t plus 2. That's what I got. If you do the dot product, you get that. And this should give you 4 over 3. That's our answer. Okay. So that's how we do line integral from what we already know. Now, how about if we decide to use Green's theorem on this? So let's use Green's theorem. Why are we using Green's theorem? Because it's a closed curve. It's a closed curve, so we can use Green's theorem. Green's theorem says that if we have a closed curve like this, and we're looking for the line integral along the boundary of the curve, the line integral can be expressed in terms of double integral whose region of integration is the open region inside the boundary of the curve, enclosed by the boundary of the curve. That's what I meant to say. So instead of breaking up the integral into separate integrals, we can use Green's theorem. F dot dr now would be the integral C. To use Green's theorem, you want to express it in terms of f dy plus g, f dx plus g dy, all right? So the first, let's look at our f. F is f is actually x, and y is F is negative y, and G is x. Okay, that's what I meant to say. So we have, we're going to use Green's theorem. I'm going to say this is f dx plus g dy, and then this is region dg dx minus df dy. Okay, that's what we're doing. So this is just the statement of Green's theorem. Just the statement of Green's theorem. Now let's work on it. So that means we can now say that the integral f is x. Nope. F is negative y, right? Is it? I just forgot. Oh yeah, negative y dx plus x dy. G is x. All right. So using Green's theorem, we're going to look at the integral over the region R. dg dx will be the partial derivative of x with respect to x. That's easy. That's just one. And then the partial derivative of negative y with respect to y. That is just negative 1, right? And the integral over dA. So let's try to do this double integral here. This would give us the double integral. Our region, look at our region. Our region is this. So y goes, this is y equals 0. And this is y, the pink line is y equals 1 minus x squared. So y goes from 0 to 1 minus x squared. And then x goes from 0 to 1. Okay. 0 to 1. And then dx is just 1, right? Dx is 1. D negative y dy is negative 1. So we're subtracting negative 1. And this is dy dx. So this should give us 0 to 1, 0 to 1 minus x of 2 dy dx. Okay. So if you keep going in this with this integral, you can factor out the 2 and do the first integration inside from 0 to x will just give you 1. Will give you from 0 to 1 minus x. Sorry about that. It's going to give you actually 1 minus x squared. What am I saying? It'll give you 1 minus x squared. And then you do the second integration, factor out the 2, you have the integral of 1 is x, integral of x squared is x cubed over 3, 0 to 1. Plug in 0, plug in 1, your answer should be 4/3. So that was the same answer we got before. So this is how we use Green's theorem. You can see that Green's theorem makes this a little easier, right? In the previous method of solving the problem, we had to break it up into 3 different line integrals over C1, C2, and C3, okay? But since we are working with a closed region, and it's a region that we can parameterize, we can actually work with a little bit easier, we could use Green's theorem, okay? And we did, and it worked. And remember that for you to use Green's theorem, the orientation of the curve has to be counterclockwise. So another one, let's evaluate the integral 4x squared plus sine y squared dy minus 4y cubed plus cosine of x squared dx, where C is the boundary. C is the boundary of the disk. R is equal to xy such that x squared plus y squared is less than or equal to 4. And this is oriented counterclockwise. So it's a positive orientation. All right. So first of all, what do we have? Let's look at our orientation, our curve. Okay. So it's a circle of radius 2 oriented counterclockwise. And we have a region. Our region of integration is this if we are going to use Green's theorem. But it's a line integral, so we are integrating along C. Now, if you look at this, you will see that this is since dy came first, this is g dy. If you're going by the notation we introduced, this is f dx plus g dy. All right, so our f is equal to negative 4y cubed plus cosine x squared. Let's take the partial. We need the partial with respect to y, which is negative 12y squared. And then our g is equal to 4x cubed plus sine of y squared. We need partial with respect to x, which will give us 12x squared. Okay? Our integral now, this particular integral that we're asked to do, all right, can now be written as integral f dx plus g dy, which Green's theorem tells us that is dg dx minus df dy dA over the region R. All right, what is this? This is the integral over the region R, 12x squared plus 12y squared dA. Okay. But now check this out. This gives us a good setup, a fertile ground to use polar coordinates. How about I just drag everything and, oh, no, that's fine. Put it here. Polar coordinates. This is a circle of radius 2, and we can factor out a 12. Okay. And we have x squared plus y squared dA. X squared plus y squared is equal to r squared. Because if you think about this, I think we've done this before. X squared is r squared cosine squared theta, and then y squared is r squared sine squared theta. And this is because x is always equal to r cosine theta and y is r sine theta. Okay, so this is going to give you factor out an r squared cosine squared theta plus sine squared theta. And this will just give you this r cosine squared theta plus r squared sine squared theta is 1. So this is just going to give you r squared. Okay. All right, so let's go back to our blue work. So we have 12 here and r, so x squared is r squared, and then we need r, dr d theta. R goes from 0 to 2, theta goes from 0 to 2 pi. Okay. if you do this integration, you end up with 96 pi. That's what I got. All right, now let's see how we can use Green's theorem to find area. Okay, so assuming we have a region. Consider this region right here. No. So this is like a random region. This is R, and R is enclosed by a curve C. So let's recall a few things. First, recall that if we want to find the area of R, the area of R is just 1 dA. Remember your double integral. If you want to find the area of a region, it's just the same thing as integrating the region over, integrating 1 over the region. So I'm going to pose a few scenarios to you. Remember Green's theorem. Don't forget Green's theorem. Now, scenario 1 is this. Assuming F, think of Green's theorem. Assuming F is 0 and G is equal to X for Green's theorem. Then our integral F dx plus G dy is just going to be integral X dy. And this is the same thing as the integral. So using Green's theorem, this is the integral dg dx minus df dy all dA. But dg dx is equal to 1. So this is just going to be the integral r1 dA. So do you see that one way of finding the area of a region is to just compute this little integral here? It will give us the area of the region. And we got that by Green's theorem. Okay? So if you try the same thing, if you let f be equal to negative y and g be equal to 0, and you play the same game we played here, you will notice that the integral f dx plus g dy is going to be the integral c negative y dy because g is 0. And this will give us, using Green's theorem, sorry, I'm supposed to put double integral here. This will give us dg dx minus df dy dA. This is going to give us the integral over r of 1 dA. Okay? Again, we have this and we have that, and they're equal. The next scenario is this. The next scenario is if f is negative 1/2 y and g is equal to 1/2 x. Then again, the Green's theorem or the line integral f dx g dy will just boil down to integral negative 1/2 y dx plus 1/2 x dy. And if you do double integral over r dg dx minus df dy dA, this will give you also 1 dA, which is the area. So we have looked at the area of the region R from different perspectives, and we've gotten 3 different line integral expression for the area. Okay? So if you want to find the area of R, you can say the area of R now is equal to the integral x dy, or you can use negative the integral y dx, or you can use negative 1/2 y dx plus 1/2 x dy, whichever you want. All right, so let's see an example. So I meant to put this in a little box. Okay. So this example, let's call it example 3. We would like to find the area of the ellipse x squared over x plus, over 4, x squared over 4 plus y squared over 1 is equal to 1. And we're given the parametric equation. The parametric equation is x of t is equal to 2 cosine t, and y of t is equal to sine t. And t goes from 0 to 2 pi. So I'm sure you've seen an ellipse in grade school. So this ellipse looks like this. Negative 2 here on the x-axis, and then on the y-axis 1, negative 1. And we're looking for the area of this region here. All right, so let's use, we can use any of the formulas above, any of this formula that we find comfortable. So we can go with the area being x dy. Okay, so that should give you the integral from x. Okay, now the integral from 0 to 2 pi, okay, x dy. X is 2, no, hold on, I don't want to confuse you. 0 to 2 pi, x is 2 cosine t, and dy is what? Dy is the derivative of y dt. The derivative of y is cosine t. Then we add a dt there. Okay? So this is a Calc 2 integral. And if you use this is just the same thing as cosine squared x. One way of expressing cosine squared x is you can express it as 1/2 cosine 2t plus 1 dt, right? Put the 2 outside there. All right, so this becomes equal to find the antiderivative 1 sine 2t plus t. Plug in 0, you plug in 2 pi, you get I think you get 2 pi. That's what you get. All right. Okay. I want to quickly introduce us to something, but I think we can stop here for now and do that another time. All right. I will see you in class. I'll talk to you in the next video.